Analysis of double line to ground fault or LLG fault. In double line to ground fault, the two line conductors contact with each other along with the ground. The causes of this type of fault is a tree falling on two of the line conductors and wherever two conductors shorted with each other along with ground. So the percentage of such type of fault is nearly 10%. Now we are going to see the steps to analyze the double line to ground fault in the power system. So step 1, draw the diagram of three-phase generator model representing the fault. Step 2, write the basic equation. Step 3, consider symmetrical component of voltage. Step 4, consider phase current. Step 5, find fault current IF in terms of the sequence current IA0, IA plus and IA minus. And step 6, find the voltage VB in terms of IA0. Then step 7, consider the phase voltage equation. Step 8, consider symmetrical component of voltage derived from the sequence network of generator. And step 9, find the zero sequence current IA0. Step 10, find negative sequence current IA minus. And step 11, find positive sequence current IA plus. Step 12, find the fault current IF. And finally, in step 13, draw the complete sequence network. Now we start with step 1. Draw the diagram of three-phase generator model representing the fault. So consider a three-phase generator with a fault on phase B and C through an impedance ZF to ground. So here we are considering phase B and C are short circuited and it is shorted to ground. So this is the double line to ground fault. The two phases are short circuited and it is shorted to ground. IB and IC are short circuited and it is grounded through the impedance ZF, and this ZF we call it as a fault impedance, and the current flowing through this path is the fault current. Step 2, write the basic equations. So for that we can consider the three-phase generator model. We are considering the fault occurs at B and C phase short circuited and it is shorted to ground. So the current at A phase equal to 0, and this two current IB and IC together joined and it is going as a fault current. Okay, so you can write IB plus IC equal to IF. And in terms of voltage, if you see, these two phases are short circuited and this point is a common point, and that is equal to the potential at that particular point is VB, and that is equal to VC. Both the potentials are same since both the lines are short circuited, and that will be equal to, this voltage will be equal to the fault current flowing through the ground, fault current into the fault impedance. So these are the basic equation we are going to consider for the analysis of double line to ground fault. So consider this equation as equation number 1. Step 3, consider symmetrical component of voltage. So the symmetrical component of voltage can be represented like this: VA0, VA plus, VA minus equal to the T inverse matrix into VA, VB and VC. And you can expand this VA0 equal to 1 by 3 into VA, VB and VC, and we know that this VB and VC are same. VB is equal to VC, so replace VC by VB. So it become 1 by 3 into VA plus 2 into VB. Similarly for the second term, VA plus and VA minus. By seeing this equation, you can conclude that this VA plus is 1 by 3 into VA minus VB. Similarly, VA plus equal to 1 by 3 into VA plus A into VB plus A square into VB again. And taking VB as common, it become A plus A square. So from the A operator rule, you know that 1 plus A square equal to 0. So A plus A square equal to minus 1. So instead of this A plus A square, you can substitute minus 1. So the value will be 1 by 3 into VA minus VB. Similarly for VA minus, you will be getting this A square plus A into VB, and that is minus. So it become 1 by 3 into VA minus VB. So by seeing these two equations, these two are same. So VA plus is equal to VA minus. That is your third equation. Step 4, consider phase current. So the phase current equation can be represented like this: IA, IB, IC equal to T matrix into IA naught, IA plus, IA minus. Expand this matrix: IA, IB and IC, IA naught, IA plus, IA minus. Similarly, IA naught plus A square into IA plus A into IA minus, and IC equal to IA naught plus A into IA plus A square into IA minus. So this is your fourth equation. Now step 5, find fault current in terms of the sequence current IA naught, IA plus and IA minus. To find the fault current, we are going to consider the equation 1. The fault current can be represented as IF equal to IB plus IC. So this IB and IC we found in equation 4. We are going to substitute that IB and IC from equation 4. So IF equal to IB term plus IC term, and in that there are two IA naught terms, so 2 into IA naught, and take IA plus as common, it become A square plus A, and take IA minus as common, it become A plus A square. And we know that A plus A square or A square plus A, that will be equal to minus 1. So substituting minus 1 here, it become 2 IA naught minus IA plus minus IA minus. Taking minus as common here, so IF equal to 2 IA naught minus IA plus IA minus. So this is your equation 5. So this is a fault current which has all the three sequence currents. So now from equation 1 and 4, so see in equation 1 and equation 4, we can write this IA equal to 0, and where IA equal to IA naught plus IA plus IA minus, and from this we can write IA plus IA minus, that will be equal to minus IA naught. So this is your equation 6. So why we are considering this, we are going to substitute this equation 6 in equation 5, the previous one. In the equation 5 we got IA plus and IA minus term together. In here we are going to substitute this minus IA naught. So substitute that minus IA naught here, and already one minus is there, so it becomes plus IA naught. So the fault current IF equal to 2 IA naught plus IA naught, that will be equal to 3 IA naught. So fault current IF, that is equal to IB plus IC, and that is equal to 3 into IA naught. This is your equation 7. So now step 6, find the B phase voltage in terms of zero sequence current IA naught. So for that we consider the first equation, and in the first equation VB equal to ZF into IB plus IC. So consider that as the 8th equation, and now we are going to substitute the 7th equation in this 8th equation. So in the 7th equation we found IB plus IC equal to 3 into IA naught. So substitute that, you will be getting VB equal to 3 into ZF and IA naught. So this is your 9th equation. Now step 7, consider the phase voltage equation. So the phase voltage can be represented like this: VA, VB, VC equal to the T matrix into VA naught, VA plus, VA minus. Expand this matrix. So from equation 3 we know that VA plus equal to VA minus, and you can substitute that. Instead of VA minus you can substitute VA plus. So VB equal to VA naught plus A square into VA plus A into, instead of VA minus you can substitute VA plus. VA naught and take VA plus as common, it become A square plus A, and A square plus A is minus 1. So VB equal to VA naught minus VA plus. So we recur VB, so that alone we are going to find. Okay, no need to bother about VA and VC. Okay, so we are concentrating on VB alone. So considering that equation alone, VB equal to VA naught minus VA plus. So this is your 10th equation. So now equate the 10th equation and 9th equation. So 10th equation is VB equal to VA naught minus VA plus, and 9th equation is VB equal to 3 ZF into IA naught. Both LHS are same, so equate RHS. So VA naught minus VA plus, that will be equal to 3 into ZF IA naught, and this is your 11th equation. Step 8, consider symmetrical component of voltage derived from the sequence network of the generator. So that equation can be represented like this: VA naught, VA plus, VA minus, that will be equal to 0 EA 0 minus the Z matrix into IA naught, IA plus, IA minus. So expand this matrix. So VA naught equal to 0 minus Z naught, IA naught, VA plus equal to EA minus Z plus IA plus VA minus equal to 0 minus Z minus IA minus, and this is your equation 12. Now step 9, find zero sequence current IA0. So substitute equation 12 in 11. So the 12th equation is VA0, VA plus and VA minus, and in 11th equation we got this VA0 and VA minus. So we are going to substitute this here. So instead of VA0, substituting minus Z0 IA0, and VA plus, instead of VA plus, substituting EA minus Z plus IA plus. So we'll be getting this equation. Here I am taking IA0 as common and taking this IA0 term to that side. The minus Z0 become plus Z0. IA0 into 3ZF plus Z0, that will be equal to this whole term minus EA minus Z plus into IA plus. So from here we can determine this IA0, that will be equal to this whole term divided by 3ZF plus Z0. This is your 13th equation and this is your IA0. Now step 10, find negative sequence current IA minus. So in the previous step we determined the zero sequence current IA0. Now we are going to determine the negative sequence current IA minus. So for that we are considering equation 3, that is VA plus equal to VA minus, and so in equation 12 we got this VA plus and VA minus equation. So we are going to equate these two. So EA minus Z plus IA plus equal to minus Z minus into IA minus. From here you can derive this IA minus equal to this whole term EA minus Z plus IA plus divided by Z minus, and here one minus term is there, so in common you will be getting the minus term, and that is your equation 14, and this is your negative sequence current IA minus. And step 11, find the positive sequence current IA plus. So we determine both the currents IA0 and IA minus. Now we are going to determine IA plus. So from equation 6 we got this equation minus IA0 equal to IA plus and IA minus. We know this IA minus and IA0, we are going to find IA plus. So IA plus equal to minus IA0 minus IA minus. So substitute IA0 and IA plus from equation 13 and 14. This two equation we are going to substitute here, and in this we are splitting this terms EA divided by this whole term minus Z plus IA plus divided by the whole term plus EA divided by Z minus Z plus IA plus divided by Z minus. So after splitting we are going to take IA plus as common. So here on left hand side we will be having one IA plus, and right hand side IA plus terms are two IA plus terms are there. So taking this two terms to that side, it becomes plus Z plus into IA plus divided by 3ZF plus Z0, and here its term also become plus. Taking IA plus as common in that term, it become 1 plus Z plus divided by 3ZF plus Z0 plus Z plus divided by Z minus. This will be equal to the remaining terms. Now taking LCM on both the sides, so the LCM will be Z minus into 3ZF plus Z0. So taking that, it will be getting this term, and this side also Z minus into is 3ZF plus Z0 as LCM, will be getting this term. So the denominator term can be cancelled. You will be getting IA plus equal to this whole term, and that will be equal to this EA into Z minus plus 3ZF plus Z0. Now IA plus equal to this whole term EA, this whole term divided by this whole term. So you can write like this: IA plus equal to EA into Z minus plus 3ZF plus Z0 divided by this whole term. So this is your positive sequence current IA plus. So further simplifying this term, in the numerator you will be having Z minus plus 3ZF plus Z0, and in the denominator you are going to take that term as a common out, that is Z minus plus 3ZF plus Z0. Take this term as common. So the denominator become Z plus Z minus into Z0 plus 3ZF divided by this whole term. Now you can cancel these two terms. So your IA plus equation become EA divided by Z plus Z minus into Z0 plus 3ZF divided by Z minus plus 3ZF plus Z0. So this is your 15th equation, and this is the positive sequence current IA plus. And now step 12. Find the fault current IF. To find fault current, we are going to consider the equation 7, IF equal to 3 into IA naught. The IA naught we derived in equation 13. So substitute that IA naught here. So minus 3 into this whole term. Okay, and this in this term you will be having this IA plus term. Okay, in the previous step we derived this IA plus term. So from the previous step we are going to substitute this IA plus here. So substituting IA plus from equation 15. So this is your IA plus term. So substitute that IA plus term here. So IF equal to this minus 3 divided by Z0 plus 3ZF into this whole term. Now taking LCM and simplifying this equation, you will be getting the final expression of IF as like this, a big equation which consists of positive sequence impedance, negative sequence impedance, zero sequence impedance and the fault impedance. So this is your equation 16. Now the last step, step 13, draw sequence network. As we seen from the fault current equation and the equation 3, 6 and 11, IA plus IA minus, that will be equal to minus IA naught, and VA naught minus VA plus equal to 3Z of IA naught, and VA plus is equal to VA minus. By seeing this equation we can say the sequence networks are connected in parallel. We can draw the three sequence network, positive, negative and zero sequence network in parallel, representing the impedances, current and voltage. Like that you can draw. So the positive sequence network can be represented like this, the induced EMF EA and ZF. The current flowing through this is IA plus, and here you will be having VA plus, and parallel to that you will be having a negative sequence network Z minus, the current is IA minus and the corresponding voltage is VA minus, and zero sequence you will be having Z0 and that will be equal to ZS plus 3Zn, and the current is IA naught, voltage is VA naught, and you will be having a fault impedance as 3 into ZF as we seen in the fault current expression. So this is how you need to analyze the double line to ground fault in power system.